welcome to this problem walkthrough. In this session, we'll tackle LeetCode number 1521, titled Find a Value of a Mysterious Function Closest to Target. This problem presents an intriguing challenge involving functions and optimization. Let's dive in and explore different approaches to solve it. Here, we are tasked with solving a problem based on a mysterious function, denoted as f, x, y. This function has three important properties. First, applying the function to the same input twice simply returns that input, meaning f, x, x equals x. Second, the function is symmetric, so the order of inputs doesn't matter, f, x, y equals f, y, x. Lastly, the function has a unique property where applying it to two numbers remains unchanged even if you apply it to their bitwise and result with a third number. This makes the bitwise an operation integral to understanding the function's behavior. Now, given an integer array ARR and a target, we need to find a value val that is calculated using the function on a subarray of ARR, such that the absolute difference between val and target is minimized. If multiple subarrays lead to the same absolute difference, any of them can be chosen. The goal is to return the minimum possible absolute difference. The output for this problem is a single integer, representing the smallest absolute difference between the mysterious function's value and the target. Let's look at an example to clarify. Consider the input array ARR equals 9, 12, 3, 7, 15, and target equals 5. We calculate f for all possible subarrays of ARR. For the subarray 9, the function value is 9, and the absolute difference from the target is 9, 5 equals 4. Similarly, for 12, the function value is 12, and the absolute difference is 7. For 3, the function value is 3, and the difference is 3, 5 equals 2. These calculations demonstrate how the absolute difference is derived for individual elements. We can continue exploring the subarrays of the array to calculate the function value and the absolute difference. For the subarray 7, the function evaluates to 7, making the absolute difference 7, 5 equals 2. Similarly, for 15, the function value is 15, and the difference is 10. When we look at multi-element subarrays, the function uses the bitwise in operation. For instance, 3, 7 evaluates to 3 and 7 equals 3, resulting in an absolute difference of 2. Among all these subarrays, the smallest absolute difference is 2. This highlights the importance of considering both single-element and multi-element subarrays when calculating the function values. In another example, consider ARR equals 4, 8, 2, and target equals 6. For single-element subarrays, 4 gives f equals 4 with an absolute difference of 2, 8 gives f equals 8 with an absolute difference of 2, and 2 gives f equals 2 with an absolute difference of 4. With multi-element subarrays, we calculate the bitwise in values. For 4, 8, the result is 4 and 8 equals 0, giving a difference of 6. Similarly, both 8, 2, and 4, 8, 2 also evaluate to 0, with differences of 6. The minimum absolute difference is 0, achieved by the subarray 4, 8. This demonstrates that the bitwise in operation is critical to narrowing down the potential values of the function. To solve this problem efficiently, we must account for the constraints. The array length can go up to 100,000, and elements and the target can be as large as 10 million. These constraints make a brute force approach infeasible because evaluating all possible subarrays would take too long. Instead, we need to leverage the properties of the mysterious function to optimize the solution. The key insight is that the function depends only on the bitwise n of the elements in a subarray. By focusing on how the n operation reduces the range of possible values, we can limit the number of computations and achieve an efficient solution. This understanding is crucial to tackling the problem within the given constraints. To solve this problem, we first explored the brute force approach, which is the most straightforward way to address it. The intuition here is simple: for every possible pair of elements in the array, compute the result of the mysterious function f, a, I, a, j, which is based on repeated bitwise in operations. Then, compare the result of this computation to the target value and track the closest match. Specifically, we iterate through all pairs I, j, where I is less than or equal to j, and for each pair, we compute the n for the subarray from a, I, to a, j. By continually updating the minimum difference between the result and the target, we can identify the closest value. However, this approach is computationally expensive. The repeated in computations for overlapping subarrays result in a time complexity of n cubed, as we're iterating through pairs and then performing multiple operations for each one. Additionally, it has constant space complexity. While straightforward, it becomes infeasible for larger input sizes due to its inefficiency. Now, to overcome the inefficiency of the brute force approach, we turn to an optimized strategy that leverages the properties of the bitwise AND operation. A key observation here is that the result of a sequential AND operation is monotonically non-increasing. This means that as you extend the subarray by including more elements, the result of the AND operation will either stay the same or decrease. Using this property, we can avoid redundant calculations by focusing only on the distinct results that arise when performing AND operations on a subarray. Instead of recalculating the AND for every possible subarray, we use a sliding window technique. During this process, we maintain a set of distinct AND results for the current subarray, ensuring that we only work with unique values. For each of these distinct values, we calculate the difference with the target and update the closest value accordingly. This approach significantly reduces the computational overhead. The time complexity comes down to n asterisk log max a, because the number of distinct values generated by the AND operation is limited. The space complexity is also reduced to log max a for storing these distinct values efficiently. Ultimately, we chose the optimized approach that leverages the monotonic property of the AND operation. The brute force method, while simpler to implement, is far too slow for larger inputs due to its n cubed time complexity. In contrast, the optimized approach takes advantage of the limited number of distinct values produced by AND operations, allowing us to focus on these key results without explicitly evaluating all possible subarrays. By iterating through the array and maintaining distinct AND results for each starting point, we drastically reduce redundant computations. This makes the solution scalable and efficient for larger input sizes. While the optimized approach is slightly more complex, it effectively balances implementation difficulty and performance. This highlights the importance of leveraging mathematical properties, such as monotonicity, to simplify and speed up computations. By avoiding unnecessary evaluations, we arrive at a solution that is both elegant and computationally efficient. To start with the brute force approach, we need to prepare the input. First, we take the array ARR and the target value target. At this stage, it's important to handle any edge cases, such as when the array is empty or contains only one element, to ensure our solution doesn't break. Once input parsing is complete, we initialize a variable called closest, which will store the value closest to the target as we process the array. This variable is typically initialized to infinity or the largest possible value, depending on the programming language, to ensure any valid calculation will be closer than the initial value. Next, we use two nested loops to iterate over all possible pairs of elements in the array. These loops ensure that every combination of elements is considered. For instance, in Python, we might use two for loops where we compute the pair a_i, a_j, and we can add a condition to exclude self-pairs if necessary. This gives us a complete enumeration of all possible input pairs for the function. Once we've established how to iterate over all pairs, the next step is to evaluate the function f, x, y. This function will be applied to each pair, a_i, a_j, that we've generated from the nested loops. The specific implementation of f will depend on the problem requirements, but it typically involves arithmetic operations, comparisons, or other computations. After evaluating the function, we compare the result to our closest variable. The goal is to check whether this result is closer to the target than the current value stored in closest. For instance, we calculate the absolute difference between the function result and the target, and if this difference is smaller than the current closest difference, we update closest to the new value. Once all pairs have been processed, the final value of closest is returned as the output. This brute force method, while simple and exhaustive, operates with a time complexity of n squared, because of the nested loops. However, it uses minimal space, with a space complexity of 1, since no additional data structures are required beyond storing the closest value. The brute force approach works because it evaluates all possible pairs in the array, guaranteeing that we find the closest value to the target. This makes it a reliable baseline solution. However, it's crucial to account for edge cases to avoid runtime errors. For example, if the input array is empty, we need to return a default value or an error. Similarly, if the array has only one element, we must handle the inability to form pairs. While this method ensures correctness for small input sizes, its inefficiency becomes evident as the array grows larger. Optimizations like sorting the array or leveraging binary search can significantly reduce the computational complexity and make the solution more scalable. Ultimately, this approach trades efficiency for simplicity, making it a good starting point for understanding the problem or benchmarking more advanced solutions. In this approach, the array serves as the primary data structure for storing input values. Arrays are ideal here because they allow direct access to elements using indices, and this simplicity aligns well with the nested loop iteration. Additionally, we use a single variable, closest, to track the value that is nearest to the target throughout the computation. This choice minimizes space usage, keeping the overall space complexity at 1. The key operations in this algorithm revolve around computing the function f, x, y for each pair, comparing the result to the target, and updating the closest value when the new result is better. These steps form the backbone of the logic. By using the absolute difference between the function result and the target, we ensure that we account for both higher and lower values. The condition for updating the closest variable ensures that only the most relevant value is retained, which helps streamline the computation while maintaining accuracy. When implementing the solution, it's crucial to handle a variety of edge cases to ensure robustness. For instance, if the input array is empty, the algorithm should return a default value or an appropriate error message to prevent unexpected behavior. If the array has only one element, we need to account for the fact that pairs cannot be formed, and the implementation should handle this gracefully. Duplicate values in the array also require careful consideration to ensure the function f, x, y behaves as expected and doesn't produce inconsistent results. Finally, negative values in the input array can impact how the function is computed and compared against the target. It's important to ensure the logic accounts for these scenarios, particularly when calculating absolute differences, to maintain correctness across all possible inputs. This Python solution aims to solve LeetCode problem number 1521, find a value of a mysterious function closest to target using an efficient bit manipulation approach. The solution begins by initializing two variables, current_set to track the ongoing results of bitwise and operations, and closest to record the minimum difference found between a result and the target value. Closest is initially set to positive infinity to ensure that any valid difference will be smaller. The input array ARR is processed element by element. For each number, the algorithm calculates the bitwise and of the current number with all previously stored values in current_set. These results are added to a new set, new_set, which also includes the current number itself. This ensures that all combinations of bitwise and operations are accounted for as the array is traversed. After updating current_set, the algorithm iterates through its values to compute their absolute difference from the target value. If a smaller difference than the current closest is found, closest is updated. The use of a set ensures that redundant values are eliminated, optimizing the number of comparisons and reducing computational overhead. The algorithm leverages the properties of the bitwise and operation, where results decrease as more numbers are combined, leading to an efficient traversal of the problem's solution space. Finally, the smallest difference, stored in closest, is returned as the result. This approach ensures that the solution is both correct and optimized for the constraints of the problem. Here, we start by importing the necessary libraries and defining the solution class with the method closest to target. The goal of this method is to find the value closest to the target by leveraging bitwise and operations on subsets of the array. We initialize a hash set called currentSet to keep track of intermediate results of AND operations. We also define a variable closest to store the minimum difference between any intermediate result and the target, starting with integer.max_value as its initial value. The next step is to iterate through each number in the given array. For every number, we create a new hash set called newSet, which will temporarily store the updated end results for this particular iteration. At the beginning of each iteration, the current number is directly added to the new set. Then, for every value already in the current set, we compute its bitwise and with the current number and add the result to new set. This ensures that all possible results involving the current number are captured. After processing all values, we update current set to reflect the contents of new set. Finally, for each value in the updated current set, we calculate the absolute difference between the value and the target, updating the closest variable whenever a smaller difference is found. At the end of the method, we simply return the closest value, which represents the minimum difference between any bitwise end result and the target. This approach is efficient because it minimizes redundant calculations by maintaining and updating the sets iteratively. By leveraging bitwise end operations and carefully managing the intermediate results, we can efficiently narrow down the closest value to the target in the given array. Here, we start by considering the array 9, 12, 3, 7, with a target value of 5. First, we initialize two variables, current_set, which begins as an empty set, and closest, set to infinity to represent the smallest difference we've found so far. During the first iteration, we process the number 9. A new set is created containing only the number 9 itself, so new_set equals 9. Next, we update current_set to this new set, making it current_set equals 9. We then calculate the absolute difference between each value in current_set and the target. Since abs 9 to 5 equals 4, we update closest to 4, as it's the smallest difference we've encountered so far. In the second iteration, we process the number 12. A new set is created, starting with just the number 12, so new_set equals 12. We then compute the bitwise end of each value in current_set with 12. For the value 9, 9 and 12 equals 8, so we add 8 to new_set, resulting in new_set equals 8, 12. We update current_set to this new set, current_set equals 8, 12. Now, we calculate the absolute differences with the target. For 8, abs 8 to 5 equals 3, which is smaller than our current closest, so we update closest to 3. For 12, abs 12 to 5 equals 7, which doesn't improve the closest value. In the third iteration, we process the number 3. We create a new set containing just 3, so new_set equals 3. Then we compute the AND operation, 8 and 3 equals 0 and 12 and 3 equals 0, which means new_set becomes 0, 3. We update current_set to 0, 3. Calculating the differences, abs 0 to 5 equals 5 doesn't change closest, but abs 3 to 5 equals 2, so we update closest to 2. Finally, in the fourth iteration, we handle the number 7. A new set is created starting with 7, so new_set equals 7. We compute the AND operation for each value in current_set with 7, 0 and 7 equals 0 and 3 and 7 equals 3, which results in new_set equals 0, 3, 7. Updating current_set gives us current_set equals 0, 3, 7. Now, we calculate the differences with the target. For 0, abs 0 to 5 equals 5, for 3, abs 3 to 5 equals 2, and for 7, abs 7 to 5 equals 2. None of these values improve the closest, so it remains 2. At the end of all iterations, the closest value to the target is 2, which is our final output. Now, let's analyze a new example with the array 15, 8, 6, 4, and target value 10. Again, we initialize current_set as an empty set and closest as infinity. In the first iteration, we process the number 15. Starting with new_set equals 15, we update current_set to 15. The absolute difference abs 15 to 10 equals 5, so we set closest to 5. Next, in the second iteration, we process the number 8. A new set is created containing just 8, so new_set equals 8. We compute 15 and 8 equals 8 and add the result to new_set, keeping it as 8. Updating current_set gives us 8. Calculating the difference, abs 8 to 10 equals 2, which improves the closest value, so we update closest to 2. During the third iteration, we process the number 6. Starting with new_set equals 6, we compute 8 and 6 equals 0, resulting in new_set equals 0, 6. Updating current_set gives us 0, 6. We calculate the differences with the target, abs 0 to 10 equals 10 and abs 6 to 10 equals 4, but neither improves the closest value, so closest remains 2. In the fourth and final iteration, we handle the number 4. We create new underscore set equals 4 and compute the end results. 0 and 4 equals 0 and 6 and 4 equals 4, resulting in new underscore set equals 0, 4. Updating current underscore set gives us 0, 4. The differences abs 0 to 10 equals 10 and abs 4 to 10 equals 6 do not improve the closest value, so the final output remains 2. For the third example, we have the array 1, 2, 4, 8, and target value 6. First, we initialize current underscore set as an empty set and closest as infinity. In the first iteration, we process the number 1. Starting with new underscore set equals 1, we update current underscore set to 1. The absolute difference abs 1 to 6 equals 5 sets closest to 5. In the second iteration, the number 2 is processed. A new set is created, new underscore set equals 2. We compute 1 and 2 equals 0, so new underscore set becomes 0, 2. Updating current underscore set gives us 0, 2. Calculating the differences, abs 0 to 6 equals 6 doesn't change closest, but abs 2 to 6 equals 4 improves it, so we update closest to 4. Next, in the third iteration, we process the number 4. We create new underscore set equals 4 and compute 0 and 4 equals 0 and 2 and 4 equals 0, which results in new underscore set equals 0, 4. Updating current underscore set gives us 0, 4. The differences abs 0 to 6 equals 6 and abs 4 to 6 equals 2 show an improvement, so we update closest to 2. In the fourth and final iteration, we handle the number 8. A new set is created as new underscore set equals 8, and the end results are 0 and 8 equals 0 and 4 and 8 equals 0, leaving new underscore set equals 0, 8. Updating current underscore set gives us 0, 8. The differences abs 0 to 6 equals 6 and abs 8 to 6 equals 2 do not improve closest, so the final output remains 2. To analyze the time complexity of this solution, we start by examining the outer loop that iterates over each element in the array ARR. If the array has n elements, this loop contributes an O(n) factor to the overall complexity. Next, within this loop, the algorithm updates the current underscore set by performing bitwise AND operations between the current number and all values in the current underscore set. The size of current underscore set is limited by the number of bits and the largest value in the array, which is proportional to log max RR. This happens because each bitwise AND operation progressively reduces the number of set bits, limiting the distinct results. Therefore, updating the current underscore set adds an O log max RR factor for each element in the array. Finally, for each value in the current underscore set, the algorithm calculates the absolute difference with the target and updates the closest value. Since the size of current underscore set is again at most O log max RR, this step also contributes O log max RR for each element in the array. When we combine these steps, the overall time complexity becomes O(n) for iterating over the array multiplied by O log max RR plus O log max RR for updating the current underscore set and finding the closest value. Simplifying this, we get a total time complexity of O(n) asterisk log max RR. For space complexity, the key consideration is the space required to store the current underscore set. As we discussed, the size of the current underscore set is bounded by O log max RR. Additionally, the algorithm uses a constant amount of space for auxiliary variables like closest and new underscore set, which contribute O(1) space. Therefore, the total space complexity is dominated by the storage of current underscore set, resulting in a final space complexity of O log max RR. To better understand the efficiency of this solution, let's compare it to a naive approach. In a brute force solution, we would calculate the bitwise and for all possible subarrays of ARR and then find the closest value to the target. Since an array of size n has O(n) squared subarrays, and calculating the n for each subarray involves iterating over its elements, the time complexity of the brute force approach would be approximately O(n) cubed. In contrast, the optimized approach avoids explicitly iterating over all subarrays by leveraging the current underscore set to track only distinct results from bitwise AND operations. This reduces the time complexity to O and asterisk log max RR, which is a significant improvement. Analyzing specific cases, the best case scenario occurs when all elements in the array are identical. Here, the current underscore set remains of size 1 throughout, making the time complexity O n. On average, for random inputs, the current underscore set size grows logarithmically with the number of bits in the maximum value, leading to O and asterisk log max RR. Even in the worst case, the current underscore set size cannot exceed log max RR, so the time complexity does not worsen beyond O and asterisk log max RR. The bound on the size of the current underscore set is a direct result of the nature of bitwise and operations. With each operation, the number of set bits in the resulting values is reduced, meaning that the distinct results produced by repeated AND operations are limited. This behavior ensures that the current underscore set cannot grow indefinitely. In fact, its maximum size is proportional to the number of bits in the largest value in the array, which is given by log max RR. This mathematical property is what allows the optimized solution to efficiently keep track of the necessary results and maintain its logarithmic complexity in terms of the maximum value in the array. When working on problems like this, there are several common mistakes to watch out for. First, overlooking edge cases can lead to incorrect results. For example, edge cases might involve empty arrays with just one element, or arrays with duplicate values. These scenarios can behave differently than expected, so it's important to account for them during testing. Another frequent issue is using inefficient pairwise computation. While a naive nested loop might seem straightforward, it can cause significant performance issues when the input size grows large. Optimizing these operations can save you from timeouts on larger test cases. Next, misunderstanding the constraints provided in the problem is a trap many fall into. For instance, ignoring the range of input values or whether the elements must be distinct can lead you to design solutions that don't align with the requirements. Hard-coding results is another pitfall. While it may work for specific test cases, it often leads to code that fails on unseen inputs because it isn't generalized. Finally, ignoring numerical overflow, especially when working with very large numbers, can result in unexpected errors, particularly when performing arithmetic operations. Always keep these common pitfalls in mind to ensure your solution is robust and efficient. Now, let's turn our focus to some key interview insights that can help you approach similar problems effectively. First, always clarify the function or operation described in the problem. For instance, ask whether it is associative, commutative, or has any specific properties that could simplify the computation. Understanding these details can sometimes reveal opportunities to optimize your solution. Look for patterns or properties within the problem itself. Sorting the input array, for example, might simplify pairwise computation in certain scenarios. It's also important to communicate with your interviewer about the trade-offs between brute force and optimized approaches. Demonstrating that you understand the time and space complexity of various solutions shows depth in your problem solving. Additionally, breaking the problem into smaller, manageable components and solving each incrementally can highlight structured thinking. This approach not only makes the solution more manageable but also helps illustrate your thought process clearly, which is something interviewers value highly. Finally, it's helpful to explore related problems and alternative approaches to strengthen your problem-solving toolbox. For example, the two-sum problem on LeetCode focuses on pairwise operations and introduces hash maps for optimization. The three-sum problem builds on this by finding triplets instead of pairs, adding another layer of complexity. Longest consecutive sequence is another great example where array manipulation and efficient techniques are key. Additionally, subarray sum equals k demonstrates how prefix sums can optimize what initially appears to be a brute force problem. As for alternative approaches, brute force methods are easy to implement but are often inefficient for large inputs. They're best used for small constraints or as a baseline to compare optimized solutions against. Sorting-based optimizations, on the other hand, can be powerful. For example, sorting can enable the two-pointer technique, which reduces the time complexity significantly. Hash maps or sets are also invaluable for optimizing lookups and tracking scene values, often reducing complexity from O(n) squared to O(n) in many scenarios. Lastly, a divide-and-conquer strategy can sometimes be the key to solving problems involving range queries or merging operations efficiently. By considering these related problems and techniques, you'll be better equipped to tackle a variety of challenges with confidence. Great job making it to the end of this session. Today, we unraveled the mystery behind the function and explored how to find the closest value to the target efficiently. Remember to keep practicing similar problems and refining your problem-solving skills. Thanks for watching, and we'll see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!